Installing a 34.5 kV medium voltage supply line with a 3-80 square mm XLPE cable inside a 3-100 square mm rigid steel conduit or RSC can lead to several probable consequences. Firstly, thermal overheating is a major concern. The smaller XLPE cable will carry a higher current density than it was designed for. This increased current density results in an elevation of the cable's temperature. The enclosed RSC further restricts the heat dissipation process, causing excessive heating. This can lead to potential installation damage over time, reducing the lifespan and reliability of the cable system. Secondly, conductor damage is another potential issue. The confined space within the RSC may subject the conductor to mechanical stress. This stress increases the risk of conductor breakage, particularly during installation or due to vibrations and movements over time. The smaller cable size may also result in higher voltage gradients, which can potentially damage the conductor insulation. Thirdly, the installation can lead to a reduced current carrying capacity. The thermal limitations of both the XLPE cable and the RSC will limit the overall current carrying capacity of the feeder. This reduction in capacity can hinder the power transfer capability of the system or cause overloading during peak load conditions. Exceeding the cable's current carrying capacity can accelerate the degradation process and create unsafe operating conditions. Fourthly, premature insulation failure is a significant risk. The combination of high temperature and mechanical stress can significantly accelerate the degradation of the XLPE insulation. This accelerated degradation can lead to premature failure of the cable, resulting in unexpected downtime and costly repairs. In addition to these consequences, it is essential to consider relevant code provisions. IEEE Standard 1220.2012, which is the IEEE Guide for Transmission Line and Substation Structures, provides guidelines and recommendations for the design and construction of these systems, including cable installations. IEEE Standard 1584.2018, which is the IEEE Guide for Conductors and Dissimilar Metal Connectors in Electrical Power Distribution, offers information on conductor selection and installation practices. NFPA 70.2017, the National Electrical Code, or NEC, contains specific requirements and regulations for electrical installations to ensure safety and compliance. The NEC addresses cable sizing, conduit fill, and other relevant aspects of cable installation. To address the situation, several recommended actions should be considered. Firstly, inspect the installation thoroughly for any signs of overheating, conductor damage, or insulation degradation. This inspection can help identify any existing problems or potential issues that need to be addressed. Secondly, conduct load flow studies to verify the suitability of the current feeder configuration and its current carrying capacity. These studies can help determine if the cable is properly sized for the expected load and operating conditions. Thirdly, consider replacing the smaller XLPE cable with a cable of appropriate size for the RSC. Selecting a cable that is designed to handle the current and voltage requirements of the system can mitigate the risks associated with overheating and conductor damage. Fourthly, installing cooling devices or ventilation systems to improve heat dissipation within the RSC can help reduce the cable temperature and extend its lifespan. Fifthly, monitor the feeder temperature and load regularly to ensure safe operation. This monitoring can help detect any potential problems early on and allow for timely intervention. These steps contribute to a safer and more reliable electrical system. The current carrying capacity of a cable is influenced by several factors, including the cable's material, size, insulation type, and the surrounding environment. Generally, cables made of materials with higher conductivity, such as copper or aluminum, can carry more current than cables made of less conductive materials. The larger the cross-sectional area of the cable, the more current it can safely carry. Different types of insulation have different temperature ratings, which affect the cable's ability to dissipate heat. The ambient temperature, proximity to other heat sources, and whether the cable is installed in free air or in a conduit all affect its ability to dissipate heat. The NEC provides tables that specify the allowable ampacities of cables based on their size, insulation type, and installation conditions. These tables are used to ensure that cables are not overloaded, which can lead to overheating and fire hazards. When a cable is overloaded, the excess current generates heat within the cable. If the heat is not dissipated quickly enough, the cable's temperature will rise. Excessive heat can degrade the cable's insulation, reducing its ability to withstand voltage and increasing the risk of a short circuit or ground fault. Overloading can also cause the cable to sag or melt, creating a fire hazard. The NEC specifies the maximum allowable ampacity for different sizes and types of cables. It also specifies deterring factors that must be applied when cables are installed in certain conditions, such as when they are bundled together or installed in a hot environment. Deterring factors reduce the allowable ampacity of a cable to account for the reduced ability to dissipate heat. When selecting a cable for a specific application, it is important to consider the expected load, the ambient temperature, and the installation conditions. The cable should be sized to handle the expected load with an appropriate safety factor. It is also important to ensure that the cable is installed in accordance with the NEC and any other applicable codes or standards. Conduit fill refers to the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC specifies the maximum allowable conduit fill to ensure that there is adequate space for the conductors to dissipate heat and to allow for easy pulling of the conductors during installation. Overfilling a conduit can lead to overheating of the conductors, damage to the insulation, and difficulty in pulling the conductors. The NEC specifies different fill limits for different types of conduits and different numbers of conductors. For example, the maximum allowable fill for a conduit containing 3 or more conductors is typically 40%. This means that the total cross-sectional area of the conductors in the conduit cannot exceed 40% of the conduit's cross-sectional area. The cross-sectional area of a conductor is calculated based on its diameter. The diameter of a conductor is typically specified in the NEC or in the manufacturer's specifications. When calculating the conduit fill, it is important to include the cross-sectional area of all conductors in the conduit, including insulated conductors, neutral conductors, and grounding conductors. The NEC provides tables that can be used to determine the maximum number of conductors of a given size that can be installed in a particular size of conduit. These tables take into account the conduit fill limits and the cross-sectional area of the conductors. When installing conductors in a conduit, it is important to use appropriate pulling lubricants to reduce friction and make the pulling process easier. It is also important to avoid kinking or damaging the conductors during installation. If the conduit is overfilled or if the conductors are damaged, it may be necessary to replace the conduit or the conductors. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to the conductor's resistance. Voltage drop can cause equipment to operate inefficiently or not at all. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. The amount of voltage drop in a conductor depends on several factors, including the conductor's resistance, the length of the conductor, and the amount of current flowing through the conductor. The resistance of a conductor depends on its material, size, and temperature. The longer the conductor, the greater its resistance. The higher the current, the greater the voltage drop. Voltage drop can be calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance. To minimize voltage drop, it is important to use conductors that are large enough for the expected load. It is also important to keep the length of the conductors as short as possible. In some cases, it may be necessary to use multiple conductors in parallel to reduce the resistance and voltage drop. The NEC provides guidelines for calculating voltage drop and for selecting conductors that will minimize voltage drop. These guidelines should be followed to ensure that equipment operates efficiently and safely. Grounding is the process of connecting electrical equipment and systems to the earth. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect people from electric shock and to prevent damage to equipment. The NEC requires that all electrical equipment and systems be grounded. There are two main types of grounding systems: system grounding and equipment grounding. System grounding is the grounding of the neutral conductor of an electrical system. Equipment grounding is the grounding of the non-current carrying metal parts of electrical equipment. System grounding helps to stabilize the voltage of the electrical system and to provide a low impedance path for fault current to flow back to the source. Equipment grounding helps to protect people from electric shock by providing a low impedance path for fault current to flow back to the source, which causes the circuit breaker or fuse to trip and to energize the circuit. The NEC specifies the requirements for grounding electrical equipment and systems. These requirements include the size and type of grounding conductors, the methods for connecting grounding conductors, and the location of grounding electrodes. It is important to follow the NEC requirements for grounding to ensure that electrical equipment and systems are properly grounded and that people are protected from electric shock. Bonding is the process of connecting together all of the non-current carrying metal parts of electrical equipment and systems. Bonding helps to create a low impedance path for fault current to flow back to the source, which helps to protect people from electric shock and to prevent damage to equipment. The NEC requires that all electrical equipment and systems be bonded. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that are used to connect together the metal parts of electrical equipment. Bonding jumpers must be sized according to the NEC requirements. The NEC also specifies the methods for connecting bonding jumpers. It is important to follow the NEC requirements for bonding to ensure that electrical equipment and systems are properly bonded and that people are protected from electric shock. Short circuit current is the high current that flows in an electrical circuit during a short circuit. A short circuit occurs when there is an unintended connection between two or more conductors in an electrical circuit. Short circuit current can be very high, and it can cause damage to equipment and injury to people. The NEC requires that electrical equipment be protected against short-circuit current. Short-circuit protection is typically provided by circuit breakers or fuses. Circuit breakers and fuses are designed to interrupt the flow of current in an electrical circuit when the current exceeds a certain level. The interrupting rating of a circuit breaker or fuse is the maximum amount of short-circuit current that the device can safely interrupt. It is important to select circuit breakers and fuses with interrupting ratings that are high enough to protect the electrical equipment from short-circuit current. The NEC provides guidelines for calculating short-circuit current and for selecting circuit breakers and fuses with appropriate interrupting ratings. Arc flash is a dangerous electrical hazard that can occur when there is a short circuit or other electrical fault in an electrical system. An arc flash is a sudden release of electrical energy that can cause severe burns, blindness, and even death. The NEC requires that electrical equipment be designed and installed in a way that minimizes the risk of arc flash. Arc flash protection is typically provided by arc-resistant switchgear, arc flash relays, and personal protective equipment, or PPE. Arc-resistant switchgear is designed to contain the energy of an arc flash and to prevent it from spreading to other equipment. Arc flash relays are designed to detect an arc flash and to quickly trip the circuit breaker to interrupt the flow of current. PPE is clothing and equipment that is worn by workers to protect them from the hazards of arc flash. The NEC provides guidelines for assessing the risk of arc flash and for selecting appropriate arc flash protection measures. Safety is paramount when working with electrical systems. Always de-energize circuits before working on them. Use properly insulated tools and equipment. Wear appropriate personal protective equipment, including safety glasses, gloves, and arc-rated clothing. Follow all applicable codes and standards. If you are not qualified to work on electrical systems, hire a qualified electrician. Electrical safety is everyone's responsibility. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or other professional before making any decisions about electrical systems.